Okay, this is our final exam review for Math 125, but this video contains material that we only covered on Test 3 and Test 4. I wanted to work through a few problems. Okay, first let's start with asymptotes, finding the asymptotes. Okay, for this one, find the equation of any vertical asymptotes, and then we want to find horizontal or slant. Okay, so if you remember, for vertical asymptotes, you want to see if by chance, let's see, this can be factored. I don't know if it can, but for vertical asymptotes, see if the rational function can be simplified. Let's see, we have a 3 and a 1. Actually, negative 6 plus 1. It actually does factor, but it doesn't help us at all because you can't cross any common factors out. So it really doesn't help us. But for vertical asymptotes, remember, they're the only, you just set the denominator equal to 0 and solve. So if we set that equal to 0, we get x equals negative 2. This is my vertical asymptote, and you must write it in the form of x equals. All right, x equals negative 2. All right, for part B, determine whether it has a horizontal or slant. Okay, let me copy this down again. Remember, for horizontal asymptotes, we have our quick way that you can look at it. Remember how we look for horizontal. You can compare the leading terms, 2 over 1. Remember the rules, because you could be asked any of this. If the degrees were the same, then my horizontal would have been the coefficients in front, which would have been 2 over 1. Let's see, if it had been larger in the denominator, like maybe 2x squared over x cubed, then my horizontal would have been 0, y equals 0. But this one, if you notice, it's larger in the numerator. We have 2 as the power in the numerator and only 1 in the bottom. So there is no horizontal asymptote. Okay, no horizontal. But there is a slant asymptote. So we need to find the slant. And the way you do it is you can divide the fraction, divide the bottom into the top. All right. So x right here goes into 2x squared, 2x times. And let's see, let's multiply it out. Don't forget to subtract. When you subtract each term. That gives you negative 9x. And then now one more time, x here goes into negative 9x, negative 9 times. Okay, you can finish it out if you want to. And if you subtract, you change both signs, you get a remainder of 15. Okay, so for slant asymptote, the remainder has nothing to do with it. Your slant asymptote is what the quotient is. So my answer would be B. There is no horizontal asymptote, but the slant asymptote is y equals 2x minus 9. Okay, for this question, we want to solve the rational inequality. This is the one that we have to use the sign chart. Okay, so since it is a fraction, we need to find the interval endpoints. And the way we find it is you can set the top equal to 0 and the bottom equal to 0 and solve. So if I set the top equal to 0, give ourselves room, add the 2x over, we get x equals 3. Okay? So that's the top. I'll mark it right there. The 3 makes the numerator 0. And if we set the denominator equal to 0, 2x plus 3 equals 0. I get x equals negative 3/2. Negative 3/2. Those are my two interval endpoints. So now let's do our number line. We're going to plot the interval endpoints. We had negative 3/2, which is what, negative 1.5. And then we have positive 3. Okay, so now if you remember this is where we put dotted and straight lines. Since it's a fraction, you've got to remember the denominator the one that made the denominator 0, is always dotted. So the negative 3/2, we're going to do a dotted line. That is because it can never be part of the solution, because it makes the denominator equal to 0, and that is undefined. All right, but now the 3, we can draw a straight line. Okay, because my problem is asking where is this greater than or equal to 0. 3 is the only value that makes this function equal to 0. So it's part of the solution. Okay, but we have our 3 intervals. Now we just need to test the region. I'm going to recopy because this is what we are plugging into. Here's my function. All we care is, are the intervals positive or negative? So let's start something less than negative 3.5. I'll pick like negative 4. If you plug negative 4 into the function, you get, what, 6 minus, and if you were to plug in negative 4, like that, you get 6 plus 8 is positive, right? And then negative 8 plus 3 is negative. So we have a positive divided by a negative gives me negative. So that whole interval is negative. Let's do the same for the middle interval. I'm going to pick 0. If I plug 0 into the top, I get, what, 6 minus 2 times 0, and 2 times 0 plus 3. So that's 6 minus 0, and then 0 plus 3. You get positive divided by positive is positive. And then finally, let's plug in 5 or something like that. So we have, what, you can look at it, 6 minus 2 times 5 is 10. 6 minus 10, 2 times 5 plus 3. We have 6 minus 10 is negative, and then 10 plus 3 is positive. Negative. Okay, so these are my regions. The two negatives are the intervals that make this function less than 0. Positive makes it greater than 0. So since I'm looking for, up here in the problem, greater than 0, the positive is what my answer is going to be. So my answer is going to go anywhere between, in this little area right here. And my answer will be negative 3/2 to 3. Remember, a parenthesis because of the dotted line, right? And a bracket because of the straight line. This is my answer. Okay, let's look at the exponential equation. Our goal here is to relate the bases, right? And so if we can write them in terms of the same base, we'll be able to solve it. So let's look at 49 to the x, and 1/7. All right, well, we know that 49 is the same as 7 squared. So I'm going to recopy that. And then we know that 1/7, we can bring 7 to the numerator, right, just by writing as 7 to the negative 1. So I'm going to rewrite that. And so now we have 7 and 7 as our bases. So let's rewrite it again. 7 to the 2x. And then 7 to the negative 1 times x minus 4. All right. So we have our 7s are the same. Therefore, now we can just set our powers equal to each other and solve it from here. All right. Let's finish it off. We have to distribute through. And I'm going to add x to the other side. So I get 3x equals 4. X equals 4/3. So for the next one, we're solving a log equation. Okay? So for the log equation, remember we have to get rid of the log in it. And since it's set up as log equals a number, we have to convert to exponential form first. Convert to exponential. So remember how we do that. We start with the base, 3. Remember 3, we raise it to the 3. We do a counterclockwise little circle. So 3 cubed equals 3x minus 8. And this is what we have left to solve. So with the little bit of space I have left, let's finish that off. 3 cubed is 27. I'm going to add 8 to the other side. What's that, 35? All right, and finally, divide out by 3. We get x equals 35/3. So now we're dealing with logs, and all they're wanting us to do is to expand the log expression. We're not solving anything, we're just expanding it using our expansion rules. So for this one, before we start, I'm going to go ahead and multiply 1 over 216 times x. If you do that, you get x over 216. We did this in our test. This just makes the process a little bit easier. So now we want to expand. Okay, so if you remember, let's see, I forgot the base. We got to write the base. Log base 6. If you're dividing the terms, you can split them into 2 logs by subtracting between the logs. There we go. And then they want us to evaluate the log wherever we can. Right? So of course we can't do anything with log base 6 of x. But log base 6 of 216, let's see if we can write that. 216 is 6 cubed. 6 times 6 times 6. And remember the rules, if you have the same bases, then this whole thing simplifies to 3. So our final answer would be log base 6 of x minus 3. Now the next problem is just turn around and go in the opposite direction. We're going to combine into a single log. Okay, so we're going to first start by going backwards. Before we can combine, we have to get rid of the number right in front. Write that. So what we can do is bring the 6 back up, the 3, and the 5. So let's rewrite it. That'd be the natural log of x to the 6th, log of y cubed, the natural log of z to the 5th. Now we're ready to combine into one log. The natural log x to the 6th times y cubed. Because of the subtraction, you divide out z to the 5th. This is my final answer. Okay, so now the one at the top is our last one before we get into all the trig. Okay, so here we have 9 to the x equals 4. This is an exponential where we can't relate the bases. So what we have to do in this case is we can take the natural log of both sides. So if I did that, I'll say the natural log of 9 to the x equals natural log of 4. Okay, by doing that, you can take the x and bring it down in front. That's one of the rules of logs. So we can rewrite that as x times the natural log of 9 equals natural log of 4. And finally, to finish, we're solving for x. So let's divide out by natural log of 9. This, when they ask for the exact answer, this is what we're talking about. Natural log of 4 over natural log of 9. Okay, we won't be able to do decimals because we don't have a calculator to find the decimals. But that's all they want. Okay, now we move into test 4, which is all of our trig. So hopefully this won't be quite as, old to you since we just covered this. But to find the exact value of the cosine of 7 pi over 6, we can use our unit circle. Remember what we do. You can just look up 7 pi over 6, which would be right here. You remember the point that's right by 7 pi over 6. The first term represents cosine, the second represents the sine. Since they're asking for cosine, my answer is right there, negative square root of 3 over 2. Okay, this happens to be very similar. They're asking for cosine again of 11 pi over 6. So let's come to our unit circle. Here's 11 pi over 6. Our cosine is the first term. So that is square root of 3 over 2. That's my cosine. Let's see. The second one, they asked for the sine of 11 pi over 6. It's the same circled angle. Remember, the second term represents sine, so our sine in this case would be negative 1 half. That one's right there. The sine of 11 pi over 6 is negative 1/2. All right? And finally on this one, they're asking for the cosecant of 5 pi over 6. So let me come over here so I have a little more space right here. So for the cosecant, remember this is where we have to find the reciprocal first. Cosecant and sine are together. Let's find the sine of 5 pi over 6. Then all we have to do is flip the answer. Sine of 5 pi over 6, let's look it up on our unit circle. 5 pi over 6. Remember the sine is the second term. That would be 1/2. So sine of 5 pi over 6 is 1/2. Therefore, the cosecant, you flip it, you get 2 over 1. My answer is 2. Okay, let's do, let theta be an angle in standard position. Name the quadrant. Okay, remember they give us the two pieces of information. We're going to use our all students take calculus chart. So for the first one, the cosine is greater than 0. So where is the cosine positive? We know our cosine is positive in the first and the fourth. Now let's do tangent. Tangent is greater than 0, so that's positive. Tangent is positive in first and third. Therefore, theta lies in the one that satisfies both situations, which would be quadrant 1. Okay, so if you remember this from the test, this is the one where you have to write it in the algebraic expression. This is where we have to put this on a right triangle. So remember, let's start first inside the parenthesis. Let's rewrite this. This is the same as saying the cosine of theta equals 5u. Now we know that cosine is adjacent over hypotenuse, right? So adjacent over hypotenuse. Sorry, let's go over here. Let's create our right triangle and let's put theta right there. Okay, so our hypotenuse is the long one. Opposite is the side that's opposite theta, right there, opposite, and adjacent is the other. So for this, cosine at the adjacent would be 5u, and the hypotenuse would be 1. We need to find the opposite, and let's use the Pythagorean theorem. Pythagorean theorem says the two smaller sides squared should equal the longer side or the hypotenuse squared. Let's solve for the opposite. So 5u squared is 25u squared. And 1 squared happens to be 1. So opposite squared is 1 minus 25u squared. And finally, let's square root both sides. So my opposite side is represented by 1 minus 25u squared. Okay, so let's finish it off. We know that my original problem says the tangent, and then inside that parenthesis, that was represented by theta. Well, let me write that way, theta. Okay, now we rewrote the value for cosine, right? It's 5u over 1, and we found the opposite side by using Pythagorean theorem right over here. Okay, so now the tangent, we know by definition the tangent equals opposite over adjacent. So, theta, the opposite side, we found to be 1 minus 25u squared, the square root. And the adjacent, remember, was 5u. So this is my final answer. On these problems, you need to show your work here. Okay, obviously, if you just wrote the answer, you will not get any credit for this. I need you to show me how you got this. Okay, now we get to the inverse trig function. So if you remember, sine and tangent inverse work the same way. So in this case, if we had the sine of negative 1/2, we only have one possible answer. Our answer is going to be a theta. And what you do is let's come and look up the reference angle. So come down to our chart. Sine is, well, square root of 2 over 2, which remember, this is the right here. That's the same thing as writing this as negative square root 2 over 2. We just have it rationalized. Those are the same angles. So sine at pi over 4 is where this happens. So my theta, my reference angle, is pi over 4. But remember, since we had a negative number right there, my angle is negative, which means it's a quadrant 4 angle. So it's just the reference angle, and you just carry the negative down with it. The same thing works for tangent. So let's just do another example here. If I had inverse tangent, let's see, of 1 over square root of 3. Inverse tangent, you just come over here and say, well, the tangent is 1 over square root of 3 at pi over 6. My reference angle is pi over 6. Since 1 over square root of 3 was positive, my angle is positive. If I had given you the same question, except it was negative 1 over square root of 3, your answer would have been negative pi over 6. Okay? Right here, these two examples of inverse tangent show you the difference. Positive goes with positive, and negative goes with negative. And the same thing works for the sine, inverse sine. Okay. Okay, so now when we get to inverse cosine right here, this is the one that's different. I'm asking for the inverse cosine of negative 1 over square root of 2. So just like right before, that is the same thing as saying I want to find the inverse cosine of negative square root of 2 over 2. It's just another way of writing the same angle. So remember, cosine is different. Because this is negative square root of 2 over 2, we have to write a quad 2 angle, quad 2. So you come down here and you say, okay, where is cosine square root of 2 over 2? It happens at pi over 4. That's my reference angle. Okay? But for cosine, you cannot bring the negative down. You have to write this as quad 2. And pi over 4 is the reference angle. The quad 2 angle is 3 pi over 4. Okay, let's find the solutions. These are the equations that we're finishing up with. For these, my answers are from anywhere from 0 to 2 pi, which is the whole unit circle. So we have to take into account the whole thing. Previously, with the inverses, you only had one possible answer, either from one quadrant or the other. But this represents all 4 quadrants. So let's see, we have the tangent. We're going to solve this. Let me add square root of 3 to the other side and get positive square root of 3. We're trying to find theta. Okay, so we tell ourselves the tangent of theta equals positive square root of 3. That's positive, right? So we just ask ourselves, where is tangent positive? Tangent is positive in the first quadrant and the third quadrant. So my theta has got to be a quad 1 angle and a quad 3 angle. But let's figure out what the reference angle is. You can use our chart down in the lower left-hand corner of the page. Tangent is square root of 3 at pi over 3. So my reference angle is pi over 3. That happens to be my quad 1 angle. Okay, that's that one. And then for my quadrant 3 angle, we still use the same reference angle, which is pi over 3, but we write it as quad 3, which is 4 pi over 3. These are my 2 possible angles to solve this equation. Okay, let's look at the next one. Find all the solutions for the following. So let's look. We want to solve this for sine of x, right? So it's just like working an equation. Let's bring square root of 2 to the other side. So we get 2 sine x equals positive square root of 2. And we want sine by itself, so let's divide it by 2. Okay, so let me write it over here with a little more room. These cross out. So the sine of x equals square root of 2 over 2. And it's positive. So this is where we want to solve. Our x in this case is our theta. So we ask ourselves, the sine of x equals positive, but this is positive. So we say, okay, well, where is sine positive? All students take calculus. Sine is positive in the first and the second quadrant. So my answer for x in this case, which is my angle, like my theta, and a lot of them they're referred to as theta, but this one is x. We know that we need a quadrant 1 and a quadrant 2 angle. So let's come over to our chart and let's find our reference angle. Remember, we're looking for where is the sine equal to square root of 2 over 2. So here's sine, here's square root of 2 over 2, and it happens at pi over 4. So quadrant 1 is pi over 4. That's easy. And then quadrant 2, as you remember, quadrant 2, the numerator is 1 less than the denominator. So these are my two possible answers for the solution for this equation. I hope this helps. This finishes it up. This is not everything, but it is a really good summary of different topics throughout the whole semester. So this is a great way to just prepare for the exam.